Well, here's some things that were going on in the Hesperian. I already told you about the intense volcanism that occurred on the Tharsis Bulge, and I want to go into a little bit on the outflow channels next. But before I do that, I'd like to talk about argon isotopes. Don't panic. It's all very simple. We all know what an isotope is by now. Isotopes are chemicals with variations in their neutrons. And so we're looking at 36 argon, which has 2 less neutrons than 38 argon, and we're looking at that ratio. Now, why do we look at argon? We look at argon because it's a noble gas, and noble gases do not react with other chemicals. And so we do that because we don't want to have the argon 36 and the argon 38 behaving differently during chemical reactions. What we want to be doing is we want to be seeing processes that separate 36, 38 other than chemical processes, and that's why we've chosen argon. You'll see why in just a minute. We have the argon ratios from the Sun and Jupiter. That's considered primordial argon. We don't think that the argon ratio has been disturbed much since the solar system was formed in Sun and Jupiter. So we can take those as the original argon ratios in the solar system. Look at Earth. Earth has a slight argon, a lower argon ratio than Jupiter and Sun. What's caused that? Well, we think that some gases have escaped from the Earth, neon and other noble gases, which tend not to react with other elements, so they can escape rather easily. And here's the key. The key is that argon 36, which is lighter than argon 38, would escape more easily than argon 38. So you'd expect from escaping gases due to the solar wind or to any process, and there are several processes which I won't go into, that cause the gases to escape out into space, they would preferentially take argon 36 and therefore lower the argon 36 argon 38 ratio, and so that's why Earth is probably a little bit lower than the Sun and Jupiter. Now what about Mars? Well, we sent Viking up there, and it was worthless. It came up with a whole range of argon 36, 38 ratios. Couldn't tell much from it. Now we measure argon 36, 38 in meteorites that we think came from Mars. Maybe this is the first time you've heard that we have meteorites from Mars. We have meteorites from Mars. We have them from the Moon. We have them from a particular large meteorite, or I should say the asteroid Vesta, and we have them from other asteroids out there too. What happens is you have impacts into the surface of Mars or the Moon or whatever, and then it throws out material out into space, and some of that material makes its way to Earth. We find it. We say, hey, this has got a chemical composition of Mars. So we can look at the isotopes in there, and we know that it must be from Mars, or we have a good idea. More about that later on, but trust me, we know pretty confidently that we have Martian meteorites, a rock from Mars. And so we can look at the argon 36-38 ratio. Maybe, by the way, you remember a while back where one of these Martian meteorites, they claimed they found fossil evidence of life, single-cell life. It was later found out that it wasn't substantiated by later testing, and so it's been dismissed. But that's what we looked for life in, were those meteorites. Well, that thing called SAM that you're seeing there in the diagram, that's a sample that the rover took. SAM stands for Sample Analysis on Mars. I don't know where they get these names. Anyway, in 2013, they took that sample, and it gives us a very clear depleted argon 36-38 ratio. This indicates to us, and you already knew this from our earlier discussion, that the Mars atmosphere has been depleted. And it's, to explain that 36-38 ratio, we have to surmise that Mars has lost at least 50% of its atmosphere, and I'll be honest with you, it's probably more like 90% of its atmosphere. It's been sloughed off into space. So that goes absolutely with what we've been learning about rain on Mars. I mean, just about the time the atmosphere disappears, or most of the atmosphere, the clouds disappear, the rain disappears. So after the atmosphere was lost, the main source of water appears to be groundwater. And I'll tell you why we think this. This is one of the earliest pictures taken on Mars. It's of the Nergal Vallis, and you might think, oh, that looks like a dendritic stream pattern, but it's not. It's a very special kind of stream pattern. And if you walk up those valleys, you won't walk up into lots of little tiny valleys. You'll walk up to a wall. I mean, a cliff face, a box canyon, if you will, at the end of the stream. Big cliffs. So then geologists said, whoa, this has to happen on Earth. So they started looking around, and sure enough, we find these in arid regions. The box canyons that you see out west probably had this kind of process taking place. It's where water seeps out of the ground in rocks. You know, water travels through rocks, travels downhill, so it'll flow out of the rock and onto the ground, and it'll do erosion just like this. So we think that this kind of stream pattern, which we see in the Hesperian and even into the Amazonian, was due to groundwater seeping out. We call that water sapping, if you will. And it's a process that occurs here on Earth, and it occurs in arid regions, and we see it happening on Nergal Vallis area. Now, we also see it associated with these huge outflow channels. Look at the size of these outflow channels around the Tharsis Bulge. I mean, my gosh, these things are gigantic. You see them at the edge of the Valles Marineris, and you also see them up there in the north. A couple of large ones coming up, but I want you to follow those stream patterns back up and see where they land. The big old cliff faces up here, I've circled in black, where the water probably came from. Cliffs, well, you don't have water flowing down cliffs because you erode the cliffs. The only explanation we can come to, and by the way, these are not valleys, really. They're gigantic cliffs. You know, probably I don't know how big, thousands of meters long. So you can't explain that through flow erosion. The only thing you can explain that from is water coming from groundwater, and it's got to be plentiful. It looks for all the world like there's flooding going on there. So how the heck do you get flooding from groundwater? Well, take a look at where we are. We're in the Tharsis Bulge. The groundwater on Mars is probably frozen. So you've got frozen groundwater. You've got magmas pushing up the Tharsis Bulge. You got a lot of heat generated. So you're probably melting that ice, and you're melting it very quickly, and you're generating lots and lots of water very fast. That water comes flowing out of the rock or sands or wherever it's located, and it rolls down the hill in these gigantic floods. Let me take you in close now to these outflow channels in the Kasai Vallis. If I were to take you to the best place where you can see outflow channels just like this, I would take you to eastern Washington, and I'd set you down where there used to be a fantastic lake about 13 to 17,000 years ago. I wasn't alive then, but geologists can tell from what we see out there. It looks just like this, except for the craters. Gigantic floods occurred out there. That lake, which existed 13 to 17,000 years ago, was probably formed when a glacier put a terminal moraine up there. The water got stopped from flowing, built up a big lake behind it. The lake topped the natural dam, and it flooded all of eastern Washington. They're called the scablands, and we know from intricate studies out there that they were formed by massive flooding. And I swear, it looks just like what we're seeing here in Mars. Let me show you a close-up. I could put you in the scablands, and you'd have a hard time telling me the difference between the scablands and this picture, except for the craters. So it's a really great map or picture of the outflow channels, a close-up of the outflow channels, and look at the teardrop patterns on there, all kinds of cool stuff. And this final map, I just want to show you, the water seems to be going down these outflow channels and into the North Pole Basin. So it wouldn't surprise me if there was an ocean or a lake there. Take a look at those channels. They all seem to disappear, so they're not eroding below, or they're not eroding the North Polar Basin. So there might have been water. We think there was water. The water was probably frozen most of the time. It sublimated away eventually, but those outflow channels look like they're flowing into the North Pole Basin, and so it looks for all the world like Mars had an ocean on it, back at least in the Hesperian, maybe even into the Amazonian. And we find evaporites, sulfide evaporites, which are indicative of evaporation, or in this case sublimation, because the surface of Mars is cold. So I would conclude from this then that the groundwater produced enough water probably to form that North Pole Basin ocean, if you will, and wouldn't surprise me if we had an ocean sitting on Mars, maybe an ice ocean, if you will. Let's take a look at what we've done with water and detecting water on Mars. This actually is a satellite that went out and tried to measure the amount of hydrogen in the surface of Mars. It measures hydrogen, but really the hydrogen's bound to water. If it was hydrogen gas, it'd all escape out. So we know it must be bound to hydrogen. So the best bet is water. If you see the purple up there in the north, that's the polar ice cap. Then look at the North Polar Basin. It's got a lot of hydrogen. The dark, of course, means there's more hydrogen up there, the darker blues. And so the North Polar Basin looks like it's got water below in the subsurface. And gosh, that makes sense if you had an ocean up there and it all sublimated away, but some seeped into the ground, it'd be up there frozen today. And that's what this is telling us. Same in the south. And look at the Tharsis Basin. This is kind of cool. That it's the area that was uplifted. It probably lost all its water through those outflow channels, and it's showing the least water. The browns show the least water in the subsurface. And look at the Nowakian, those cratered areas. They also have a lot of water, and that's where we found the streams flowing along. So not surprised that we're finding water in the ground up or in the central part and the sides of the map.
Take a look at the image now in the upper left-hand corner from the Phoenix lander. The lander had a shovel that came out and actually scooped into the Martian soil and exposed these white layers, which we believe are water ice. And if you look in the upper right-hand picture, this is a meteorite impact, a very recent one, that's exposed what looks like ice at the bottom of the crater. So these are two more examples of where we have water in the Martian soil.
Things going on in the Amazonia, a little bit of volcanism. We have the polar ice caps, we'll talk about those, and then well, I want to talk about glaciation next. Show you some glaciers here. So we have glaciers on Mars, the good news is. I mean, it's a lot of stuff on Mars that we have here on Earth. Thank God, because we recognize what they are. But these glaciers are a little bit different in that they have dust in them. Look at how much dust is in there. These glaciers flowed down from the mountains. They flowed out here, and they deposited their material. Then they have dust storms on them, and it's great that dust covers the ice, and it protects the ice water from melting or sublimation. So that's probably how they're preserved on the surface of Mars. And then finally we have the poles. The poles are made of layers of ice with dust in between. We know from that hydrogen map that there's water below the carbon dioxide ice that forms. It varies depending on the seasons. Mars's axis is tilted about 25 degrees. In the past it's been as much as 45 degrees. And so that creates seasons on Mars, and we have variations then in the size of the polar ice caps due to whether it's summer or winter on that side of the planet. And you have layering. So probably we had a layer of ice lay down, and dust storms. You know, there was a dust storm when we first went and sent a satellite to Mars to take pictures. We had to wait around for that dust storm to disappear. It was about a year we had to wait to get good pictures. So we know that there are dust storms on Mars, and it's not surprising that these glaciers, polar ice caps, have dust in them. Well, I would be remiss if I didn't talk a little bit about life, the potential for life on Mars. We have made a Herculean effort to try and find out if Mars has life. You know, you probably won't be surprised at this. When I told you about impacts and sending out meteorites, and we have rocks from Mars and the Moon, it also happened to Earth probably. When we first formed life on Earth, probably there were impacts that struck Earth and sent meteorites out into space, and they landed on Mars, and maybe they were carrying earliest life forms from Earth to these other planets. It wouldn't surprise me at all that we would have single-cell creatures that hit the planet. We've actually sent single-cell life out into space, and they've lived there for years, and then we brought them back and we've revived them. So we know that life is tenacious, it can live in space, it makes its way to these planets, perhaps, wouldn't surprise me at all. And if they hit the bottom and the conditions were right, and maybe it hits a Noachian period, then you can get life existing on Mars. Maybe it's still in the groundwater. So we did go into Mars and we did take some measurements, and this is an example. Sol here means day, and we're looking at the methane concentrations. The instrument on board was measuring the methane concentration. It would take in some gas from the atmosphere, and it did it periodically, as you can see from the calculations. Now here's the thinking. Archaea on Earth, there are the most ancient single-cell forms on Earth. We think that they formed when the atmosphere on Earth was terrible for us. No oxygen in it, methane, nitrogen, all kinds of terrible things in it, carbon dioxide. But they thrived in that kind of environment. Today they live in things like septic tanks, they live in swamps, they live in your stomach, your gut. So they live in the mid-ocean ridges where the hydrothermal vents come out. So they're really tenacious, but they don't like oxygen, and they stay away from oxygen. So you get that sour egg smell or rotting egg smell. That's methane. And methane, these archaea, they have carbon dioxide and hydrogen. If you look up there at that equation in the top corner, and it reacts to form methane and hydrogen, methane and water plus energy. So that's how they get their energy, from carbon dioxide. So the scientist working on Mars said, hey, let's go look for methane on Mars, because if the bacteria is like what we think it is, this simple archaic archaea of bacteria, then we'd expect it to be giving off methane. Let's measure methane. So that's what they did. And look, they got a variation. I'm here though to tell you that that variation isn't much. Look at the concentrations. Those are parts per billion. So that means for every one atom of methane, we've got a billion atoms of something else. So I should say molecule of methane. We've got a billion of something else there. So that's not much. We have a maximum of 10 parts per billion methane. That's very little. So what's the conclusion? The conclusion, I'm sorry to say, is that we have no evidence at this point for life on Mars. This can be explained by natural processes. I don't think it's evidence for life on Mars. And yet this will not stop people from looking. I think we're going to see some more spacecraft going to Mars and looking once again for life and continuing to look for life. Who knows? I wouldn't be surprised if we found it there. It's just that we're not seeing any evidence yet of it.